Hello everybody, Mr. C here. I hope everyone's doing okay despite the stresses of the last few weeks of high school. It's the home stretch, you got this. And in this video today, we'll be doing the Calc AB Unit 4 multiple choice. So there's 10 questions. I'll try to go through them relatively quickly. But if you need help on certain ones, but not all of them, I will put timestamps on the video so you can just skip to the questions that you need extra assistance with. So let's jump in. This one wants us to find the limit as x approaches infinity of this equation here, e to the 2x over x squared. And we can start this by using L'Hopital's rule. We can see, or sorry, by using direct evaluation, right? The first method we use for trying to evaluate limits doesn't always work, but when it works, saves us a bunch of time. So let's try that. So when we plug infinity in here to the numerator, we have e to the 2 times infinity, right? That's really just e to the infinity. And on the denominator, right, we have infinity squared. So e to the infinity, that's going to be infinity, and infinity squared, that's infinity. So I kind of spoiled it, my bad, but we have infinity over infinity. This means we can use L'Hopital's rule. And L'Hopital's rule, right, we take the derivative of the top and the derivative of the bottom, and that is equal to this original limit. So this limit by L'Hopital's rule is equal to limit as x approaches infinity, stays the same, of, well, the derivative of e to the something is itself, but we need the chain rule because this is not just an x. So we need to multiply this by 2. Okay, so the derivative of e to the 2x is 2e to the 2x. And the derivative of the denominator, right, it's just power rules. So we decrease the power by 1 and multiply by the old power, so 2x. And we can see here that these cancel out. And if we try direct evaluation again, right, we just plug in infinity, we get e to the 2 infinity, which is e to the infinity over infinity, which again is the same as infinity over infinity. So again, we use L'Hopital's rule. So by L'Hopital's rule, right, the original limit is equal to this limit, which is equal to a new limit as x approaches infinity of the derivative of this top. So the derivative of e to the 2x, right? We canceled the 2. So e to the 2x has a derivative of the same thing as before, which is 2e to the 2x. And the derivative of x is just 1. So when we try direct evaluation, we get 2e to the 2 times infinity. Well, e to the 2 times infinity, that's the same as e to the infinity in the limit. E to the infinity, that's going to give us infinity. And then 2 times infinity gives us infinity. So the answer here is infinity, which is D. If you didn't want to do all that, there's a little trick here. Although this doesn't take too long, so if you're unsure about this trick, I would say just do L'Hopital's rule, but an exponential grows faster than any quadratic or any power. So if we have a polynomial, it doesn't matter what the power is, it's always going to grow slower than an exponential. I'm not going to focus too much on that here. Okay, so moving on, if we go to the next one. So in this triangle, the base of the triangle is x, and it changes at a constant rate with respect to time. We want to find the differential equation that describes the relationship between the rate of change of the acute angle here, theta, and the rate of change of the base, which is x. So we need a differential equation that relates these two. First, let's just find an equation that relates the two variables. Forget about the rates for a second. Is there an equation that relates these two variables? Well, the answer is yes, right? So using our trig knowledge, right? SOHCA TOA being opposite over adjacent, we can say that these two are related by the tangent of theta is equal to the opposite side, which is 5, over the adjacent side, which is x. Okay. But we want to relate the two rates. Our rates, as it says here, right, the base of the triangle x changes at a constant rate with respect to time. Let's say that the rates are dx dt, right, the change in x per unit time, and d theta dt, the change in theta with respect to time. Okay, so how do we do this? Well, we need to differentiate both sides with respect to time, or in other words, do implicit differentiation. We have an x in the denominator here, so before we do that, though, I'm going to rewrite this just because I like my powers in the numerator. So something divided by x is the same as something times x to the -1, right? We can move this from the denominator to the numerator by negating the exponent. And as mentioned, right, I'm going to take the derivative with respect to time of both these things. I can do this because it's doing the same thing to both sides. We don't violate any algebra laws. So when I take the derivative with respect to time of tangent theta, the derivative of tangent is secant squared theta. But we don't have t here. We have theta, so we need to use chain rule. And the derivative of theta with respect to time, well, that's d theta dt. So this is good, right? We need d theta dt in our expression. We're trying to relate these two things. Similarly, if we take the derivative with respect to time of 5x to the -1, well, we can use power rule, right? So the power comes down. So we have -1 times 5, or -5x to the, well, we have power rule for derivatives, so we need to decrease the power by 1. So we get -5x to the -2. But we're not finished, right? We differentiated this with respect to time. Our variable was x, so we need to incorporate the change in x into this with respect to time. In other words, we need to do chain rule and include dx dt here. Okay. And finally, to get it to look like a form that's given here, you can rewrite this as secant squared theta times d theta dt equals, well, just like I put the power in the numerator before, I can put the power back in the denominator, doing the same thing. So this is -5 divided by x to the 2, right? We negate the power and put it in the denominator. And that's this times dx dt. So this is our final answer, which is choice D, I believe. Okay, for question 3, we're going to let f be a differentiable function such that f of 4 is 8 and f prime of 4 is -1. It says if the tangent line to the graph of f at x equals 4 is used to find an approximation of a 0 of f, that approximation is something. Okay, so we are looking for a tangent line before anything. And more specifically, we're looking for a tangent line at x equals 4 for f. Okay, so the equation for a tangent line, we can use point slope form. Way back from algebra. So point slope form is y minus y1 equals m times x minus x1, where x1, y1 is a point and m is the slope. So what's our point? Well, we're given that f of 4 is 8. So we could rewrite that from function notation here to in ordered pair. Well, what was the x coordinate? It was 4. What was the y coordinate? It was 8. So we have our point. And what's our slope? Well, the derivative at this x coordinate is -1. So the slope of the tangent line is the derivative at that point. So in this case, m is going to be -1. Now we just plug stuff in. So we have y minus y1, which was 8, equals m, which was -1, times x minus x1, which was 4. And if we solve this for y real quick, right, we get, well, -1 times x is -x, -1 times -4 is +4. And then we add 8 to both sides. So we get y equals -x plus 12. Okay, so we found the tangent line. Why do we need to do this? Well, we want to approximate a 0 of f. A 0 of f is where f equals 0. In other words, where our y coordinate equals 0. So all we do is set y equal to 0 for our tangent line, and then solve for x. So if I add x to both sides, I get x equals 12. So at x equals 12, our tangent line is saying that f has a 0 there. We might not actually have a 0 there. This is an approximation, but that was what we were asked to find. Moving on. Okay, so let me zoom out a little bit. That's too much. All right, that's probably fine. Okay. At a professional football game, fans are allowed to enter the stadium beginning at noon for a 1 o'clock game. The number of fans that enter the stadium is modeled by the piecewise differentiable function n of t shown above. So this is n of t. Which of the following statements is false? So let's just go through one by one and see which one's false. For part A, the instantaneous rate of change at 3 p.m. does not exist. Okay, so what is 3 p.m. on our x-axis? This is the first step to reading this graph. Well, this is the time after noon. So at 0, we're at noon. So this would be noon. I'm just going to write 12. 1 hour, right? This is in hours. Afternoon will be 1 o'clock. 2 hours afternoon would be 2 o'clock. 3 hours afternoon would be 3 o'clock. 4 hours afternoon would be 4 o'clock. Okay, so we're looking for 3 p.m. So we look at 3 p.m., we look at this graph, and we want to determine if the instantaneous rate of change exists at this point. Well, we have this like corner kind of thing, right? Instantaneous rate of change refers to a function being differentiable at that point. So we're trying to find out if there is a single derivative at this point. And if you remember from way back, when we have a corner or some sort of thing that is not smooth here, right? We have this corner here. If we can draw multiple tangent lines through that same point, then it is not differentiable at that point. So there's one tangent line, but look, I can draw another one and still only hit one point. So since we can draw multiple tangent lines through this, this is not differentiable at this point, meaning there is no instantaneous rate of change at this point. So this part A is true. If you don't want to remember all that, just remember that if we have some sort of corner, we do not have a derivative at that point. And that's what instantaneous rate of change means. Okay, for part B, the units of the derivative of a function n of t is number of fans. Sorry about the motorcycle. So the units of the derivative of the function n of t is number of fans. So we're looking for the derivative of n of t being number of fans. But wait a second, this is n of t, this whole thing that they gave us. And what are we measuring n of t in? Well, it's the number of fans. So that means the derivative of n of t would be the number of fans with respect to time. So this one is false. It's false because n of t is number of fans. That means dn of t cannot be number of fans, or the derivative of n of t is not number of fans, it's number of fans per time. Okay, I do want to go through the next ones in case you don't see that one right away. So part C, there is a time between noon and 12:15 for which n prime of t is 60,000 fans per hour. Okay, so this one requires mean value theorem. So mean value theorem states that there exists some C. There exists some C between A and B. These are X values, where F prime at C is equal to F of B minus F of A over B minus A. And importantly, this only holds when F is continuous on the closed interval A to B and differentiable on the open interval. Differentiable on the open interval. So we don't need the endpoints here. Okay, so first let's check these conditions. Is F differentiable? Is F continuous on A to B? Well, this whole function here, it is piecewise, but it is continuous. Is it differentiable? Well, it's not differentiable here, right? Because this is an endpoint. So again, we could draw a bunch of different tangent lines through here. So we don't have a single derivative here, right? There's infinitely many tangent lines that go through there. So we know that it's not differentiable at that point, but we don't need it to be, right? If we're taking, I'm just gonna get rid of these for clarity's sake. If we're looking between noon and 12:15, we're looking in this region here. Sorry, this region here, right? So at X or T equals 0.25, that's the same as T equals a quarter. And right, we're measuring these in hours. So a quarter of an hour is 15 minutes. So we're looking at this interval here. So we're not differentiable here. We're also not differentiable here for the same reason as part A being true, right? We could draw a bunch of tangent lines through here. It's like a line and then a line, but it's not the same line. So there's a bunch of tangent lines going through here. So the conditions hold. F is continuous on from 0 to 0.25, but it's differentiable from 0 to 0.25, excluding 0 and 0.25. So these hold. That means there is some C such that F prime of C, whatever it is between 0 and 0.25, is equal to F of our B, which is 0.25, and F of our A, which is 0. And again, B was 0.25, A was 0. So if we solve this, F of 0.25, that was 15,000. Minus F of 0 was 0. Another way we can write 0.25 is a fourth, and that means we can write this over 1 and flip the denominator and multiply. So 15,000 over 1 times 4 over 1. Well, 15 times 4 is 60, and we have 3 extra zeros divided by 1. This is F prime, so this is number of fans per hour. So did we answer the question? This is asking us, is it true or false? There is a time between noon and 12:15 for which n prime of t is equal to 60,000 fans per hour. Well, we just showed that that is true. We do not know what C is, but we know that it must exist by the mean value theorem. So C is true. D, fans entered the stadium at a rate of 120 fans per hour between 12:15 and 12:30. So if we look at 12:15 and 12:30 and we find the average rate of change, right? We can tell if this is true or not. So again, 12:15 is when we're at 0.25 because that's a quarter of an hour after noon. Same thing, 0.5 corresponds to half an hour after noon. So that would be, so 12:15 and 12:30, that's this interval here. So we use average, find the average velocity, not velocity, sorry, find the average rate of change between these 2 points. We can just use basically this part right here. So the average rate of change, right? We have f of 0.5 because that's half an hour after 12 minus f of 0.25 because that's 15 minutes after 12 divided by just the points here. And this is our average rate of change. Okay, so now we just plug stuff in. What was f of 0.5? F of 0.5 was 45,000 and f of 0.25 was 15,000. So we have 45,000 minus 15,000 divided by a half minus a quarter is a quarter. Then we can do the same kind of thing before, right? 15,000 minus, 45,000 minus 15,000 is 30,000. We can write that as 30,000 over 1 divided by a fourth. Again, we can flip it and multiply. So we get 30,000 times 4 is indeed 120,000. And it's an average rate, so we have fans per hour. So fans entered the stadium at a rate of 120,000 fans per hour between 12:15 and 12:30. That is true. And finally, at 3:45 p.m., fans were leaving the stadium at approximately 963.33 fans per minute. Okay, so per minute here. We've been doing per hour. That's how everything's measured in this problem, right? These are hours. So at the end, we're going to need to mess with this a little bit to get it per minute instead of per hour. Okay, so doing the same exact thing we did before, we can use this average rate of change thing. The average rate of change at 3:45. We can just assume it's going to be this, the average between these two endpoints here. This looks like a line, so let's do it. Let's use these two endpoints. So let me get rid of these unnecessary lines so we can actually read it. So our endpoints are 4, 0 and 3, 57,800. Sorry, that's at 3, not 3.5. So these are the 2 points. And again, we use the same formula as we just did. Find this average rate. So f of 4 minus f of 3 divided by 4 minus 3. So 4 minus 3 on bottom, that's easy. That's just 1. I'm not even going to bother writing that. F of 4 is 57,800 minus f of 3 is 0. Oh, I'm sorry. I did that backwards. F of 4 is 0 minus f of 3 is 57,800, which gives us negative 57,800. But what is this number? This is a rate. and it's number of fans per hour because we've been doing everything in hours. We want this in fans per minute because the question asked us to, right? So how do we get from hours to minutes? Well, we can do this. We can multiply this entire thing by a conversion factor, right? So 1 hour is 60 minutes, right? So when I do this, the hours cancel out. And my units are fans per minute, which is what I want. So if you were to, this is no calculator, but if you were to do the long division, I'm going to save us the time here, you get negative 963.3 fans per minute. Okay, so this is negative 963.3333333. All right, so 963.33, great. Fans per minute, great. But this negative sign means they were leaving the stadium, right? If it were positive, this rate were positive, we would be entering the stadium. But since it's negative, we're leaving the stadium. All this is to say, part E is correct or is true. So that means, you know I went past the right answer, right? We were looking for the false one, but in case your eyes skip over that, it's a good idea to explain all these. Okay, for number 5. So a particle moves along the x-axis so that at any time t greater than 0, its position is given by s of t. For how many values of t is the particle at rest? So if a particle's position is given by s of t, then how do we determine if the particle is at rest? Well, we need to look at its velocity. More specifically, when its velocity is 0, we know the particle is not moving, right? So we look at when the derivative of the position function is 0. So again, we've seen this picture before, but s of t is our position. And then if we take a derivative with respect to time, we get v of t, which is our velocity. And then if we take another derivative with respect to time, we get a of t, or acceleration. Okay, so we're looking for when does v of t equal 0? This is what this question is really asking. A particle is at rest exactly when v of t is 0, even if just for a moment. So we need to take a derivative. When I first did this problem, I just started doing derivative. I did quotient rule, but we don't actually need to do that because if you look, we can factor out a t from the numerator. So t squared minus 2t. If we factor out a t, we get t times t minus 2 divided by t, and then this nice thing happens where the t's cancel out. So then we don't even need to take do quotient rule. However, if you do not see this and you do use quotient rule, you will get the same answer. So s of t is t minus 2, and we want to take the derivative of s of t, right, which is the same as v of t, the velocity. So the derivative of s of t with respect to time, well, the derivative of t minus 2 is just 1. Okay, so when is this equal to 0? Well, it's never equal to 0. 1 can't be equal to 0. This velocity is not dependent on this time. So that means this is not going to be equal to 0. So what values of t are the particle at rest? Well, it's never at rest because the velocity can never be 0. Okay. Number 6, again, no calculator. A particle is moving along the x-axis so that at time t greater than 0, its position is given by x of t. So sometimes they'll give us the position function in terms of x. Sometimes they'll call it s. It doesn't really matter. Over the interval 0 from t from 0 to 6, for what values of t is the speed of the particle decreasing? We are looking for the speed of the particle decreasing. And this is something that I mentioned today, which is Thursday. And I've mentioned the previous time we did particle motion, but we haven't seen too much of this. So I want to really hone in on this. This is probably the most important particle motion question that you can know, because they love to ask this kind of question. When is the particle's speed increasing? When is the particle's speed decreasing? So the speed of a function, or the speed of a particle, increases or is increasing when the velocity and acceleration have the same sign. Sign with a G, so plus or minus. And the speed of the particle is decreasing when they have opposite signs. Why is this the case? Well, pretend I am walking on an x-axis. That's me. We'll let this direction be forward, okay? So I'm walking, I'm going forward, right? Let's say I'm going at 1 mile an hour and my acceleration is positive. That means I'm going in the positive direction, but I'm getting quicker and quicker in the positive direction. The positive case may be more obvious than the negative case. So now let's say I'm going negative. I'm going in the negative direction. So if we take this to be positive and this to be negative, if I'm going in the negative direction, that means my velocity is negative. Okay, so in order to speed up in the negative direction, my acceleration also has to be negative. Because if my acceleration is positive, my velocity is actually getting closer and closer to 0 as time goes on. If I'm slowing down and I'm going in the positive direction, right, that means my velocity, right, I'm going in the positive direction, that means velocity is positive, but if I'm slowing down, my acceleration should be negative because it should be taking my velocity towards 0. Similarly, in the negative direction, my velocity is negative. So if I'm slowing down, my acceleration should be positive because it's taking my velocity towards 0. So that's the conceptual piece behind it. If you don't want to remember all that, just remember the tip right here. The speed of a particle is increasing when the velocity and acceleration have the same sign and decreasing when they have opposite signs. Okay, we've talked about it. Now, how do we do it? Well, we need to compare the velocity and acceleration's signs. Okay, so we need to find the velocity and the acceleration of this particle. And as we just wrote before, the velocity is the first derivative. It's the derivative of the position function. Here, we're calling it x. So velocity is the first derivative of x. And then acceleration is the derivative of the velocity. So let's find the derivative of x, which again is our velocity function. So this is the function we're dealing with. This is just a polynomial, so we use a bunch of power rules. So taking the derivative of this first term, we bring that power down and simplify. So we have a third times 3, or negative a third times 3, which is 1t to the 2. So we bring down this old power and decrease by 1. For the derivative of the second term, again, power rule. We bring the power down and multiply it to the coefficient. So 2 times 3 is 6. t to the, well, decrease the power, it's just t. And then the derivative of negative 8t is negative 8. And the derivative of 5 is 0. So this is our velocity function. Okay, so let's find the acceleration function. The acceleration function is the derivative of the velocity function. And again, we just take this derivative. So again, using power rule, we get negative 2t plus 6, and this becomes 0. So how do we find when the signs are positive and the signs are negative? Well, it's helpful to set these equal to 0, to find where they're equal to 0, and then we can just find the parts in between and look at the signs in between those points. So where is the velocity 0? Well, if we factor this, let me move this. If we factor this, we get negative. Well, I like to factor out the leading negative. However you factor is fine. We can factor this. It splits to t minus 2 times t minus 4 equals 0. So this means that t is equal to 2 and t is equal to 4 when our velocity is 0. Oops. T is equal to 2, t equals equal to 4, have v of t equals 0. Okay, we need to do the same thing for acceleration, find when it's equal to 0. If I add 2t to both sides, I get 6 equals 2t, and then if I divide both sides by 2, I get t equals 3. So at t equals 3, a of t is 0. Okay, so we found where all this stuff is 0 for velocity. We found where all the stuff's 0 for acceleration. Let's do this little graph thing, and I'll show you. We're going to look at a number line. First of all, we're looking on the interval 0 to 6. Okay, so we don't care about the whole interval. So we're starting at 0 and we're going to 6. So I'm going to draw 0 and 6 on the bottom. These are going to be t values. And on top, we're going to have v of t values. So I'm looking at the velocity function first. We'll look at the acceleration function after. So at t is 2 and t is 4, we know my velocity is 0. So if you don't remember how to read this, right, t is along the bottom here, v is on the top. I just indicated that we have our endpoints here, so we don't need to look beyond them. So the way this reads is like at t equals 2, v of t is 0. So we want to fill in the signs in these gaps. Why? Because the sign of a function only changes if it passes through 0. The sign of a continuous function anyway. So v is continuous, so if we have a plus here, then the sign could either be plus or minus, but it's not going to change plus to minus in this region here because we didn't go through 0. So we can't change from plus to minus within this region from 0 to 2 because we won't go through 0. I hope that's, I hope I explained that well enough. So what we do is we just pick a value between 0 and 2 and plug it into our velocity and check to see the sign. So I don't know, let's pick 1. So when v is 1, well, we have negative 1 squared plus 6 times 1 minus 8. So negative, or 1 squared is 1, and we have a negative 1. So that's negative 1 plus 6 times 1 is plus 6 minus 8. So negative 1 plus 6 is 5 minus 8 is negative 3. So in this whole region, not just at this point, but in this whole region from 0 to 2, our velocity function is negative. Similarly, we want to go and find a point between 2 and 4 because the sign of whatever point we choose will be the sign of the velocity function in this whole region. So let's pick, I don't know, 3. That seems to make sense. So again, we plug this into our velocity function, t negative 3 squared plus 6 times 3 minus 8. 3 squared is 9, so we have negative 9 because of this negative. Plus 6 times 3 is plus 18, and minus 8. Negative 9 plus 18 is positive 9, minus 8 is positive 1. So this is positive. That means in this whole region, it's going to be positive. We need to look between 4 and 6, and that's the last thing we need to consider for our velocity. So let's pick 5. So same thing as before, we plug in 5 into our equation. So we have negative 5 squared plus 6 times 5 minus 8. 5 squared is 25 times negative 1 out front is negative 25. Plus 6 times 5 is 30 minus 8. So negative 25 plus 30 is 5, minus 8 is negative 3. So in this whole region from 4 to 6, we have a negative velocity. All right, now we need to look at our acceleration, right? Because in order to determine if the speed is increasing or decreasing, we need to know the signs of both the velocity and the acceleration at different points. So let's do the same kind of picture, but for our acceleration function. So again, we're looking from time 0 to 6. That's all we need to consider. And instead of velocity, we're going to compare the acceleration this time. Now, the only time the acceleration was 0 was at t equals 3. So we only need to look at these 2 regions for signs. So let's look at a of 1 to determine the sign in this region. Well, a of 1, we plug in to the acceleration function here. That's negative 2 times 1 plus 6. That's negative 2 plus 6 is positive 4. And if we look at a point in this region, let's say 4, we have negative 2 times 4 plus 6. Well, that's negative 8 plus 6 is negative 2. And just so you know, they won't always alternate like this, negative, positive, negative. They will not always do that. So you do need to check in all the regions that we don't know, right? In all these regions between zeros of our velocity or acceleration function, right? Just because this one's positive, I could not assume this one's negative. In this case, it happened. In this case, all these alternated. But again, I can't stress this enough. They do not always do that. However, if you're on a time crunch for the AP exam, maybe make that assumption. But again, it does not always have to do that. So you shouldn't feel confident in that assumption. Okay, so we have all these regions. Why? Well, let me copy and paste these so we can see them in the same screen. Let's put this one here. And let's just put this one here. Okay, so this is what we're looking at. These 2 pictures tell us the signs of the velocity and the acceleration function at our interval from 0 to 6. That's the only interval we care about. Okay, so we are looking for when the speed is decreasing. Well, when is the speed decreasing? It's when velocity and acceleration have opposite signs. So we are looking for regions where these have opposite signs. So right off the bat, if we start at 0 and kind of go forward, we start with a negative velocity and a positive acceleration. This is good, but these don't line up, right? You can maybe imagine drawing this, right? So it's the acceleration is still positive from 2 to 3. Right? Similarly, right? You can imagine we're still negative in the acceleration from 3 to 4 here. So now we need to look at all these little regions. Also, right, there's a 0 there, so that one's not going to account for us if they are the same. I'll explain what I mean. So if we look at each of these regions from 0 to 2, right, we have a positive acceleration and a negative velocity. They have opposite signs. That means from 0 to 2, speed is decreasing. What about from 2 to 3? Well, we have a positive velocity and a positive acceleration. So they have the same sign. That means the speed is increasing. This is not what we want. All right, from 3 to 4 now, I'm just going region by region. From 3 to 4, we have a positive velocity and a negative acceleration. If they have opposite signs, that means our speed is decreasing. That's exactly what we want. And then from 4 to 6, we have a negative velocity and a negative acceleration. They have the same signs. That means our speed is increasing. So this is not what we want. Finally, our answer is just the combination of these two that worked. So on both of these intervals here, our speed is decreasing from 0 to 2 and 3 to 4. So that is answer choice D. All right, again, I can't stress this enough. The most asked question I've noticed about particle motion on free response 2 is this, having to do with the speed of the particle. And usually on those free response questions, just writing this kind of thing as your justification for your answer gets you a whole point. Okay, so recap, the speed of a particle is increasing when the velocity and the acceleration have the same sign at a point in time. And it's decreasing when the velocity and acceleration at a point in time have opposite signs. So it's a fair amount of work, as you can see, right? We took two derivatives, we did all these comparisons to find the sign of those derivatives on a certain time interval from 0 to 6. We did the same for the acceleration, and then we had to put it all together by comparing the signs at different values. A lot of steps. All right, but this one is a lot quicker. Let's actually zoom out a little more. So the line tangent to a graph of a twice differentiable function f at a point x equals 1 is used to approximate the value of f of 1.1. This approximation is an overestimate. They are telling us this. The approximation that we used using the tangent line is an overestimate. Right, so we use a tangent line. Which of the following could be the graph of f? Okay, so there's two ways to do this. I'm going to start with the easy way. Draw tangent lines, right? We're looking for the tangent line. So watch me draw a tangent line. Boom, there's a tangent line. Now, we can't see exactly what's happening at 1.1, which is the x value that we're trying to approximate at. But based on this curvature of the actual curve compared with the straight tangent line, we can see that 1.1 will be slightly larger than the tangent line's value. Right? So if I imagine this is at 1.1, let me zoom way in. Imagine that's 1.1. It's not perfect, right? But you can see the relationship is going to be the same. So this is fine to look at. Imagine this is 1.1. We can see that the curvature opening upwards like this makes it so that the real function is larger than the value that we get from approximating using the tangent function or the tangent line. So, right, we're looking at this point here. That's going to be the point on the curve, on the blue curve. And then this point's the one on our tangent line, right? We're looking for an overestimate. Does this give us an overestimate? No, it does not, right? Our approximation is less than the actual value. That is an underestimate. So the answer, this is not the answer. Again, let's draw another tangent line. This vertical line was just helpful to see the difference between the two. You don't need to draw that. Okay, so I'm just going to draw the tangent line for this one. I remember a tangent line hits the curve once. That's a little high. All right, so we're looking again at 1.1. You know what? I will draw a vertical line just to make our lives easier. And again, we can see that our tangent line is less than the curve, the actual function, at whatever 1.1 is here. Right? So here would be the value for our function. It's on this curve. Here's the value that we got from approximating using our tangent line. Our tangent line approximation is less than the actual value of this function, meaning we have an underestimate, meaning this is not the correct answer. We are looking for an overestimate. On to the next one. Okay. Well, this is a line, so the tangent line, if I draw it, is the line. Okay, so we don't have an underestimate, but we also don't have an overestimate, right? Our approximation will be exact because this is a line. We wanted an overestimate, not the exact value, so this is not going to work for us. All right, we're looking for a tangent line. Same story here. Let me draw it. Now let's draw this line just to make our lives easier. Again, you don't have to draw this line, but if we look here, this one's a little harder to see. Maybe I'll move it out a little bit. If this is at 1.1, I know this is clearly like larger than 1.5, right? It's more than halfway between 1 and 2, but see how the curvature doesn't change? So I could get away with putting it even further here. Put it as close as you can, but just for seeing this, I think it's easier to say, to move this a little to the right. Anyway, let's look at our points. We have, here's the point we get from our approximation. Here's the point we get from the actual function. And finally, our approximation gives us a value that is larger than the actual function's value. This is an overestimate. This is our answer, part D. Just for closure, let's look at part E. And then I'll give you a shortcut for answering these. Again, we draw a tangent line. I'm gonna need to fix that a little bit. Okay, then we look at 1.1, that's about here. So let's draw that extra line just to make things clearer for us. Clearly at this point, we have the same deal as we've seen a few times before. Here is the actual value of the function. Here is the approximation from our tangent line. The actual value of the function is larger than our approximation. So our approximation is an underestimate. We are looking for an overestimate. This can't be our answer. It's the same exact reasoning as two of the ones we saw before. Now, what if you don't want to do this? What if you want to do this really quickly? Well, the reason that all this happens is because of this bit here, that these are twice differentiable functions. Okay, twice differentiable, we're looking at concavity, right? Opening upwards, opening downwards, concave up, concave down, that kind of thing. So if we want an overestimate, we need a concave down function. So if you're good with looking at pictures of a function and looking at for information about the second derivative, not the first derivative, but the second derivative, this is opening upwards. So it is concave up. We want concave down. This one's not going to work for us. This one also is opening upwards. We want concave down, not concave up. So that's not going to work. This has no concavity. It doesn't open one way or the other. So that's not going to work for us. And this one, you can see it opens downward. And that's what we wanted. We wanted a function that opened downward. Oh, and this one opens upward. If that's not comfortable, the tangent line thing is exactly fine. It's perfectly fine. I mean, but again, if you want to think if you can identify concavity by looking at a graph, then for an overestimate, we want concave down. For an underestimate, we want concave up. Okay, if that's confusing, do not worry about it. Using tangent lines is totally fine. Moving right along. Okay, so what is the limit? Which of these limits has an indeterminate form? Okay, so if you notice, all these functions are the same, sine x over x. So let's kind of look at what happens to sine, right? Remember, sine, it goes like this forever and ever and ever. It's always oscillating between 1 and -1. Okay. X, well, that's just a line, right? Okay, so let's take these one by one and see what happens. So looking at part A, if we have the limit as x approaches infinity of sine x over x, and we use direct evaluation, right? We can see that this bottom part is going towards infinity as x goes towards infinity. But what about the top part? Well, the top part being sine x, it never settles on anything. It just keeps oscillating back and forth between 1 and -1, 1 and -1, going through points in between, as we see here, but it never breaks this range between -1 and 1. Because of the oscillating nature of sine of x, this limit does not exist. But it also isn't an indeterminate form, right? Indeterminate forms we're looking for 0 over 0, infinity over infinity, minus infinity over infinity, that kind of thing. Oscillate is not one of these three things, right? A note, there are other indeterminate forms like 1 to the, oh no, that's wrong, sorry. 0 to the infinity, I'm blanking on the other ones. We don't need them for this one. We just need to look at these three, or these are only going to be the ones playing a role. And these were the three indeterminate forms that work for L'Hopital's rule. Okay, but keep in mind, it's not telling us to evaluate these limits. Anyway, sine of x oscillates as x approaches infinity, right? It's never going to settle down. That means this doesn't exist. And if we look at part C, skipping B for a moment, it's exactly the same, except our limit is going to x to negative infinity. But really, that's going to have the same behavior. So yeah, x will go to negative infinity, whatever, but sine of x still oscillates as we keep going this direction on the graph to the left. It just keeps going. Okay, so just as the same reasoning as part A, the limit in part C does not exist, but again, is not an indeterminate form. So we can automatically cross off these two, A and C. Let's do E. Let's switch it up. So E, limit as x approaches negative pi of sine of x over x. Let's input this using direct evaluation. We have sine of negative pi divided by negative pi. Sine of negative pi using unit circle or reference table or your calculator if it's allowed. No calculator. So using your knowledge of trigonometry and the unit circle, sine of pi is 0 and negative pi is negative pi. Okay. 0 divided by negative pi is 0. Not only does this limit exist, right, but this is not, or I said that backwards. Not only is this not an indeterminate form, this limit exists, right? So this does not look like 0 over 0, infinity over infinity, or minus infinity over infinity. This is just the number 0. So since the limit exists, it's not an indeterminate form. So this one is not what we're looking for here. D looks really similar, so let's do that one. It's the same as E, except the limit is going to positive pi this time instead of negative pi. And you'll see that we get a pretty similar result here. Sine of pi using unit circle or whatever you use is 0. That doesn't look much like a 0. 0 divided by pi is 0. So by the same reasoning, right, this limit exists. We didn't need to use L'Hopital's rule or anything. D is not an indeterminate form. So that leaves E, but let's show why E is an indeterminate form. So E had the limit as x goes to 0. I said E. B has the limit as x goes to 0. So the limit as x goes to 0 of sine of x over x. Again, we can use direct evaluation. So we have sine of 0 over 0. Okay, dividing by 0. That's a good sign so far, but not what we need yet. What's sine of 0? Well, sine of 0, let's see from this picture, is 0. So we have 0 over 0. That is an indeterminate form. So B is our answer that we're looking for. Sine of 0, limit as x goes to 0 of sine of x over x is an indeterminate form. And by the way, we could solve this using L'Hopital's rule, right? But that's not what the question's asking. So let's not do that. Okay. Related rates time. If base B of a rectangle is increasing at a rate of 6.4 feet per minute, while its height is decreasing at a rate of 0.5 feet per minute, what is the correct interpretation of the rate of change of the diagonal of the rectangle at the instant when B equals 5 feet and H equals 12 feet? That's a long sentence. Let's break it down. First of all, we're dealing with a rectangle. Let me draw a rectangle. Can you believe I freehanded that? All right. The base of this rectangle, we're going to call B. The height, we're going to call H. This is how I approach every single word problem. I break it down into little pieces so that it's not just an onslaught of text that I have to deal with. We are looking at rates. And I'm going to highlight some stuff. So the rate of B is 6.4 feet per minute. And the rate of H, oh, I forgot an important piece here. The rate of B is increasing at a rate of 6.4 feet per minute, while H is decreasing at a rate of 0.5 feet per minute. Why is this important? Well, related rates deal with time, right? We can see that as in the per minute part of these rates, right? So can we translate these two sentences or these two phrases in terms of math language? The answer is yes. The base of a rectangle B has a rate of dB dt, right? The rate of change of B over the rate of change of T. And it's increasing, meaning we have a positive rate at 6.4 feet per minute. So 6.4 feet per minute. So this is how you translate words into calculus notation. We're going to do the same thing for H. We want the rate of change of H with respect to time. So that's dH dt. And this is decreasing. So we need a negative. This negative, super important. Be careful to read increasing and decreasing very carefully here. Don't read over those words and just see that there's no sign here because they love to put the words increasing and decreasing to kind of trap you. If they just put a plus or minus, it'd be easy, but they put increasing or decreasing. And what rate is it decreasing at? Well, 0.5 feet per minute. Okay, so we've translated the first part of the sentence. That's great. And now we are looking for the correct interpretation of the rate of change of the diagonal of the rectangle. So let's draw that diagonal. Let's call the diagonal, I don't know, something not D, maybe. D will be kind of confusing with all these Ds. Let's call the diagonal Q. I don't know. No, my Q's look like 9s. Sorry. Let's call it C. Why C? Well, our next step for related rates is to relate these rates. So is there an equation that relates all three of these things? The answer is yes. This is a rectangle. So this angle is a right angle. That means these are related by the Pythagorean theorem. So using the Pythagorean theorem, we have our sides squared. In this case, one of our sides is b. So b squared plus our other side squared, h squared, equals our hypotenuse squared, c squared. Okay. The order you do this in can vary the next couple steps, but let's do it this way. I think it's clear. We are trying to relate these rates of change, so we need to somehow incorporate rates of change into this equation that relates all the variables. Right, so let me back up. We related all these variables that we care about in one equation. Now we need to find a way to relate the rates. How do we do that? Well, we can do implicit differentiation. We differentiate both these sides with respect to t. Looking at this term, right? The derivative of b squared is 2b, but not with respect to b, right? With respect to t. So we need db dt as our chain rule. Similarly, the derivative of h squared is 2h, but we're differentiating with respect to t. So we need dh dt. And it's the same exact calculation, just with a different letter. The derivative of c squared is 2c dc dt. Again, we are differentiating with respect to t, so we need chain rule. We can divide everything by 2, right? That goes away, that goes away, that goes away. So we're left with b db dt plus h. Oh, I made a mistake. dh dt. I think I accidentally added a little loop there. Equals c dc dt. All right, and we are looking for the rate of change of this diagonal. In other words, dc dt when b is 5 and h is 12. So let's plug in all the stuff we know. B was 5. dB dt was positive 6.4. H was 12. dH dt was negative 0.5. We're looking for dC dt, so that should be left blank. But we don't know C, so we need to actually find C at this instant. So what is C? When H is 12 and B is 5, we can use Pythagorean theorem. So again, our Pythagorean theorem with respect to our variables here, were B squared plus H squared equals C squared. Our B was 5. Our H was 12. And our C is what we're trying to find. 5 squared is 25, plus 12 squared is 144. 25 plus 144 is 169. And if we take the square root of both sides to find C, the square root of 169 is 13 exactly. Okay, so now we know C, so we can plug that in. So we plugged all our values into this related rates equation, this equation relating all the rates we care about, except we want to find dc dt, so that one should be the only one left blank. Now we need to solve for dc dt. 5 times 6.4 is 32.5. That's not a flex, I have it written down. Half of 12 is 6, but we have negative, so this gives us negative 6 equals 13 dc dt. 32.5 minus 6 gives us 26.5 equals 13 dc dt. And divide both sides by 13 to get dc dt by itself. If you throw that in the calculator or just estimate, this is about 2. So 2.038 and some stuff. right? I think this one's calculator allowed. Yeah, so you can just put in a calculator. Okay, so we get 2.38 or 0.038. If you look at the answer choices, they just say 2. So let's look at we just care about 2. Okay, was this positive or negative? Well, we don't see a minus sign here, so it's a positive 2. Why do we care about this? Again, they're going to be looking for us to include increasing or decreasing in our answer. Notice D and C are exactly the same except for those single words decreasing and increasing. So we need to be really careful here. Also, we need to consider the units of dc dt. There are a couple ways to do this, right? All of these are lengths, right? And we know that the length of B is changing with respect to time in feet per minute. Same for H, feet per minute. So if we were to look at a rate of change of another length, it'd be the same units, feet per minute. Another way you could have done that would be to carry all your units through these calculations, but that's kind of a pain and kind of messy, maybe a little safer. So instead of 5, I would have written 5 feet. Instead of 6.4, I would have written 6.4 feet per minute, and etc. And at the end, you would find feet per minute if you did all your cancellation correctly. Oops. Okay, so this is in feet per minute. All right, so we need to write plus 2 feet per minute in terms of a sentence. So let's look at them one by one. When B is 5 feet and H is 12 feet, the length of the diagonal of a rectangle is 2 feet. Now this one's tempting. We see the right number. It's positive. But this is dealing with the length of the diagonal. That was not what we were asked to find. We were asked to find the rate of change of the diagonal, which necessarily has feet per some amount of time or distance per time, right? Emphasis on the per time bit for a rate of change for a related rates problem. So A is trying to trick you. This isn't a rate at all. Length of 2 feet. Feet isn't units of a rate. Feet is units of a length. Our units are feet per minute. That is a rate. We have a per amount of time. So that's a rate with respect to time. Okay, again, our answer was plus 2 feet per minute. This says 13. That's not our answer. Again, they're trying to trick you here though, right? Because we saw a 13 in our answer, but this was the length of our diagonal, not the rate of change of that length at a certain time. So they're trying to trick you. Same thing for E, right? We have 13 here. Our answer was 2, not 13. So we're between these two answers. When B is 5 and H is 12, the length of the diagonal of the rectangle is decreasing at a rate of 2 feet per minute. We wanted increasing, not decreasing, because our rate was positive. That's exactly what D says. It says increasing at a rate of 2 feet per minute. So D is our answer. If you would like a more in-depth review about related rates, please see my earlier video on related rates. I did a couple videos going through quite a few examples of related rates in much more detail than this. All right, we almost made it. Last one, another particle motion problem. This one is calculator allowed. That might or might not be helpful. A particle moves along the x-axis so that any time t is greater than or equal to 0, its position is given by this s of t here. What is the acceleration of the particle when t is 2? This one's actually the nicest of the particle motion problems we've seen today. I'm going to rewrite s of t so that we don't have dividing by a variable, because I don't like that. You know me by now. We can do that by negating the exponent and moving it to the numerator. So these are equivalent. 1 over t is the same as 2 to the negative 1. Why did I do that? Well, I know we need to take a derivative, right? In fact, we need to take a couple derivatives. Our position is s of t, and if we were to take a time derivative, we get velocity. And if we take another time derivative, that's just another way of saying if we take a derivative with respect to time, we get a of t. So take the derivative of the position, we get velocity. Take the derivative of velocity, we get acceleration. Let's do it. So velocity is the same as the derivative of this. So let's find the derivative of s of t. Well, this is just power rule. So we have negative 2t plus, the power comes down, right? So we have negative 1 times, let me write it like this, negative 1 times t to the negative 2, right? We have to decrease our power by 1. All right, if we clean this up a little bit, we get negative 2t minus t to the negative 2. We want to take another derivative because we're looking for acceleration. So the derivative of our velocity function, derivative of negative 2t is just negative 2. The derivative of negative t to the negative 2, well, if we keep this negative there, we bring down our power and we decrease our power by 1. That's a 3, ugly 3. Okay, we can do some simplification. So we have negative 2 minus a minus gives us a plus 2 to the t, 2t to the negative 3. And if we want to work with, I think it's actually easier to do like arithmetic with these in the denominator. So let's put it back. We can move this t to the negative 3 to the denominator by negating the power. So negative 3 gives us positive 3. Okay, so that's our acceleration function, but we want exactly the acceleration when our particle is t equals 2. So we plug in 2 for our acceleration. So here was a t, now it's a 2. We have negative 2 plus 2 divided by what's 2 to the 3? It's 8. 2 over 8 is the same as 1 over 4, which is the same as 0.25. I'm getting ahead of myself. And negative 2 plus negative 2 plus 0.25 is negative 1.75. And is that an answer? Of course it is. Hooray. So this is our answer. This is the acceleration of the particle when time t equals 2. Okay. Anything else I want to say about this? I think that's it. Okay. Thank you so much for watching and for your attention and your hard work this semester. It's almost done. Y'all got this. I'm proud of all you for sticking with it. You got this.